Warm good afternoon to all. It gives me a great pleasure to welcome every one of the international webinar on quantum materials and nanoparticles for advanced application. First of all, I thank Almighty for making me help to step forward in what to do. I am grateful our management for encouraging permitting us conduct the webinar, invited our president secretary for making me what I am today. I happily welcome to our principal, Dr. D. Nagarajan, who is the man of the vision. He constantly encourages us to achieve the success in all our activities. I extend my hearty welcome to Dr. A.M. Tony Melvin, Director, Self-Finance Courses, for his constant support. I extend red carpet resource person for today's webinar. I gladly welcome Dr. Professor Binay Kumar. Has nearly 30 years of experience of postgraduate teaching and research in the Department of Physics and Astrophysics of Delhi University. He has been proven many technologically important crystals, nanostructures, ceramics, etc., and used for the fabricate piezoelectric devices. He has published over the 160 research papers in international journals, guided the 18 students for PhD degree, give the more than 60 talk in the various conferences, and served as a reviewer many journals published by Nature, Elsewhere, RSC, etc. He has completed 77 major research projects and happens to be expert chairperson of various funding committee. The Postdoctral Researcher, National Taiwan University, Taiwan. The present talk, synthesis and crystal grow of quantum materials for advanced applications. Both our research persons are very novel researchers. They are deeply knowledgeable and interested in this research. They have been invited as researchers in many foreign countries. Our research person to the enlightened participants with their thought, knowledge, experience, and specialists in this topic. I like to explain thank to Dr. My educator, Dr. Narayan Sami, Associate Professor of Physics, Kamaraj College, Thuthukudi, and S. Subramanian, Associate Professor, the MTD College, and Dr. P. Selvarajan, Adityanar College, and Dr. T. Balu, Adityanar College, and I gladly welcome to Ramalingam, Assistant Professor, Department of Nanoscience and Technology, Alagappa University, Karaikudi. Next, I joyfully welcome to Dr. Muthu Sendil Pandian, Research Scientist, SSN Research Center, for encouraging, supporting, and guided to my PhD successfully. It is because of I have come to good position and stand before here. Finally, I welcome all the participants who are eagerly waiting listen to the session. Once again, I welcome one and all. Now I request Dr. Binay Kumar. Now I hand over the session to Dr. Binay Kumar. Sir.
Yes.
Sir, very good afternoon, sir.
Yes, good afternoon. Are you listening me?
Okay, sir. You continue, sir. Okay, sir. Start the session, sir.
Yes, you can start. I have already shared my screen with you.
Okay, start, sir. Okay, va. Slides are come kira. Audience la paakradhu. Not audio varudane. Seven participant admit கொடுக்கணுமா?
ஆமா அட்மிட் கொடுத்தீங்கன்னா admit.
என்னாச்சு? Sir?
Yeah, is it visible?
Yes, sir. Visible, sir. Okay, sir. Continue.
So should I start now?
Yes, sir. Okay, continue, sir. Okay.
Okay. Good afternoon, everybody. It is a pleasure for me to give a lecture on this platform. The topic is nanoparticles and single crystals for piezoelectric green energy. And I am thankful to all the organizers of this international webinar, and particularly Dr. Kannan, who persuaded me to for this lecture. So in this lecture, I will just start by introducing my crystal lab, and then crystals and nanoparticles. I will give some basic which is required for particularly the beginners in this particular field, in the field of crystals and nanoparticles. Then I will discuss what is piezoelectricity. Then with the materials we have grown as a crystal and nanoparticles of various materials, ZNO, PMN, PT, BNKT, etc. So I will discuss piezoelectricity in these materials, and then how to make a flexible thick tapes out of it for getting piezoelectric pressure sensor, as well as extracting energy out of it. The mechanical electrical conversion, that is how we can get electrical energy by mechanical pressure that comes under the category of green energy harvesting. Now, in our crystal lab, we are working on various materials, piezoelectric and ferroelectric materials, then semi-organic, non-linear optical materials, multiferroic materials, superconducting crystals, high temperature superconductors like bismuth 2212 system we have grown earlier. Then some semiconducting and polytypic material as well. We deal with various form of these materials in single crystals as well as in ceramic and nanoparticles. In our lab, we have various crystal growth and material synthesis technique for solution growth, Czechoslovsky method, chemical synthesis, and ball milling, high temperature, solution reaction, and of course, flux growth is there to grow various crystals. And in our crystal lab, we have various characterization system, piezoelectric and ferroelectric characterization system, piezoelectric charge coefficient, that is D33 meter, dielectric hardness, electrical measurement, particle size analyzer for nanoparticles, and force simulator for getting or applying force on your devices to get electrical energy out of a pressure. Just to start with very basic, how we define a single crystal. So single crystal is a solid material in which all the atoms and molecules or ions are actually arranged in a very regular way. There always exists some lattice, geometrical lattice pattern on which our atoms and molecules are sitting, so that there is a repetition of a particular area or volume which get repeated again and again in all the three directions, and this repetition extend to the till the boundary of the solid piece of material. I have just attached one big photograph of KDP crystals grown by seed rotation method by some other people. And you can see that the different faces of these crystals have very a particular angle on which all these faces and sides are meeting. The lower one is the crystals grown by us, and you can find that all these crystals represent a particular shape in which different, for example, this is a pure hexagonal one, this is almost triangular one, this is
Sir, 1 minute.
parallel one.
Sir, Ajay, sir,
Yeah.
sir, please
Yes,
change
yes,
full
yes.
full screen change, sir.
What is?
Full screen, sir. Full screen. We want to full screen, sir.
Uh, are you not seeing in my screen? It is a full screen. Are you seeing the slides? So,
Continue, sir. No
one
problem.
moment.
Continue. Okay, thank you. Continue.
No, let me again share this thing. Actually, on my screen, it is a full screen show. It is
Okay.
slideshow.
Okay, sir. Continue. No problem. Continue. Continue. Okay. Okay.
If you have, if can you take a snap and send me to my WhatsApp, then I will find what is the difference. Okay, till then I am just. Are you seeing my slide in which translation vectors are there?
Okay, sir. Okay, nice. Continue, sir. Continue, sir.
Yeah. So I'm just going back to the previous slide. So, or should I try again?
Sir.
Yeah.
Sir, continue.
Okay. So in a crystal, which is a solid piece of material, and we know that what are the characteristics of crystals. Basically, it is when the term crystal comes to our mind, various other things like a flat surfaces, specific angle between sides and planes, very characteristic colors, shining surfaces and the body. Then there is a translation vector, which is always comes to our mind when we get the crystals. Periodicity. Then,
sir, 1 minute, please change the next slide, sir. Slide is not changing. Slide is not changing.
Now it is changed.
Yes, sir. Now slide is not changing. Only first slide only available.
Only first slide is there.
Yeah. You can change the next slide. Next.
Something is wrong, because in my screen it is changing. I'm just escaping from here.
Okay. Okay, sir. I will.
Can you see my slides with
Sir? Sir?
Yeah.
Okay, sir. Continue, sir. But
no, let me know. Now, can you see my first slide?
Yeah, sir. Yeah, only first. Now okay, sir. Now okay.
This is first slide.
Yes,
now,
yes.
This is second slide.
Okay, okay. This is the second slide.
I have already discussed this slide.
No, sir. Now only this change in the slide, sir. Okay.
Okay then.
And now okay, sir. Continue, continue.
So this is a slide for introducing my crystal lab. I'm not repeating all those things. It just shows the various materials. Can you see the cursor moving on the screen?
Moving.
Okay. And then crystal, ceramic, and nanoparticles we are working. And this is a list of various characterization facility in our crystal lab. Of course, in Delhi University and our physics department, there are many equipments for characterization as a common facility. Now, this is the slide where I have tried to define the basics of crystals that in a crystal, the solid piece of this material is characterized by various very typical colors and shining. Then anisotropy is very important for the crystals. Then there is a symmetry, then Miller indices, XRD peaks, etc., which comes to our mind. I will discuss little bit one by one. Have this slide has changed now?
Slide changes. Okay, continue.
Okay. So now in a single crystals, we know that there are 7 type of habits and there are 14 types of 4 types of unit cell, that is primitive cell, and then 7 crystal classes and 14 type of Bravais lattice. I'm not going into detail, but one thing is very clear that when we think of a crystal, we think of a unit cell which is composed of atoms on a very systematic way in a cubical or rectangular basis. Now, just to understand what is a translation vector and how it is important, it is just to show that if I start with any point and move few unit cells in one direction or move in the other direction, so finally we can reach at a point which is identical with the initial point. This is one of the geometrical requirement. For example, in the lower one, this photograph, you can find there are atoms placed. So they are in a small circle area. All these atoms are placed in a regular way. So this whole is not a single crystal, but it is composed of small volumes where regularity of the placement of atoms or ions are there, but it is not extended throughout the material. So even if the small portions fulfill the criteria of a single crystal, the whole material is not a single crystal. One thing which is always comes to mind, that if we have a amorphous material, polycrystalline material, a single crystal, or a thin film, how we can differentiate between these uh, on the basis of XRD. This is XRD is the best tool to differentiate between different form of this material. So I suppose that most of the participants understand what is XRD. So when we take an amorphous is the form of material where all the atoms and molecules are randomly placed, there is no regularity, etc. So in this case, where it is an amorphous one, we don't get a peak in the XRD. Even this type of peak is many times not visible. When we have a polycrystalline material, that is the powder material of a single crystal, we get large number of peaks, which is due to Bragg's law. I'm not going into detail how these peaks are coming, but you can find a large number of peaks. Most of the students who are working on crystals or polycrystals or other form of material, they get this type of XRD peaks where 10, 20, maybe 50 peaks are there representing different directions. But what happens when we take a single crystal and place in XRD? So in that case, depending upon the direction of the basal plane, we get 1, 2, or 3 peaks, which represent a single family of peaks, like 111, 222, or 100, 200, etc. In the case of thin films, if there is some crystallinity, that is epitaxial film, we get some peaks, but in those cases, the peaks are not very of good intensity. Uh, when I say that the regularity should extend towards one end, from one end to another end of the crystal. What does it mean? It means that if I have a crystal, this is CZ grown oxide crystals, then start from one end to the other end. All the atoms and molecules inside it should follow the regularity criteria. That is, uh, all the atoms and molecules are getting repeatedly, periodically placed one by one, adjacent to each other. So this is a single crystal. Now see the middle photograph. Um, uh, in this case, you find that this is a flux grown PM and PT crystals, and we have taken it out from the platinum crucible as such. You will find that there are small pieces like this or this. So these small pieces are a single crystal, like the one on the right hand side. But as a whole, this is not a single crystal, because in this particular piece, the regularity of atoms and the sites are different from the adjoining area or adjoining volume. But when we take out one piece from it, it represents a single crystal. The left side lower photograph is a ceramic. But when you see that this is 2 micrometer, so one small grain is 5 to 10 micrometer size. So inside a particular grain, this regularity of placement of atoms and molecules are there. And so if somehow we take out one piece, this will fulfill the criteria of a single crystal, but not as a whole. As a whole, it is a polycrystalline material. The middle one of this slide, lower middle one, is a Jadano nanoparticles. Now you see this is STEM photograph. This is scanning electron micrograph. This is tunneling electron microscope photograph. You can find, if I take a jumble of nanoparticles as a whole and I make a palette out of it, this is not a single crystal. But if I somehow take one single piece out of it and take all the studies to check whether it is a crystal or not, you will find it is a good crystals, because in this small photograph you can find small dots are there, uh, which is confirming that this small rod is a single crystal. On the right hand side, this flower type of structure is a doped Jadano material, which is two-dimensional sheets are there. And this is again, if I take one sheet out of it, it is a single crystal. This is another example that if a material, this is a biphenyl crystal, Chakrovsky grown. If I crush the material and take XRD, you will find that there are 10, 20, 30 peaks of different intensity, because it is a powder material out of a single crystal. But if I cut the single crystal and take
Sir,
can you listen me?
yes, sir, yes, sir. Listen.
Uh,
But PPT is not
just
visible, sir.
okay, everything is fine. If you find that something is missing, just tell me. Because now this screen was changed to your screen. Hello,
Yes, sir, sir. PPT is not visible, sir.
your my PPT is not visible.
Yeah.
Uh,
Only your name only it is visible. Professor Binay Kumar only.
I don't know what is happening, but let me check. What you are seeing now?
Sir, PP is not visible.
Uh, uh, yes, I'm trying to find out, but uh, should I join again or something is
Okay,
wrong?
sir. Okay.
Can you see my screen?
No, sir. Only your name only it is visible, sir. Not slide is its own.
Uh, Actually, in my screen also, I'm just seeing your. Can you see my screen now?
Sir, now okay. Now okay. Sir, can you please make a full screen? Full screen. Sir, okay. It is fine, sir. It is fine.
It is fine.
Yes,
So I
okay.
was here.
Yeah, okay.
That now you can see that if I take a small piece of crystal in a particular direction and place it on XRD, only one peak is coming like this or like this. The same crystal in two different directions give single piece. So this is how we differentiate between a polycrystalline powder material and single crystal. Next slide is just to explain. Uh, is it the slide for next slide has appeared? Hello? Is that the
Sir?
slide is visible?
Yes, sir. It is visible. Very nice, sir. Okay, continue.
Yeah. So this slide is to explain a very important term that is called anisotropy. Anisotropy means that it is a very typical property of crystal that a physical property, for example, conductivity or resistivity or dielectric constant or even PL emission, they depend on the direction. So if I take a measurement of dielectric constant, these are the real experimental results of our work, that if I take a crystal and make a measurement of dielectric constant on the left hand side of one, then in different directions, we get different dielectric constant. Similarly, if I take a PL intensity of the same crystal in different directions, you can find the position of the PL peak are shifting. Similarly, the UV transmittance are very anisotropic. In one direction, it can show the transmittance of 50%, while in another direction, it is as low as 4 to 5%. So these anisotropy properties are the characteristic of crystals. This change in property in different directions are not observed when we are working on a ceramic or polycrystalline material or even a thin film. Now, a simple slide to show why we should work on crystals, because crystal represent always a brighter part of light, like purity, brightness, color, strength, etc. From ancient time, the many people are using crystals for many positive aspect of life. However, when we grow the crystals in lab, they are not necessarily a transparent or very good color or of very attractive morphology. But one thing is sure, that the crystals which we grow or the grown are in the lab are of much better physical and other properties. So crystals are important, and we must grow crystals of a specific uh, material, a specific type, and of a specific properties. So I'm just sharing some of the slides which of the crystals we have grown in recent times. This slide is for organic, semi-organic crystals. Mostly these crystals are doped crystals grown by solution method. I'm not sharing, this is TGS crystal, this is KDP crystals with some doping, this is some other crystals with different dopings. So I have selected one to show that different doping result in different morphology and different colors in the crystal. This slide is for flux-grown crystals. The left one top crystal is the PZ and PT crystals, which is very one of the best crystals in world for piezoelectricity. Right hand side, this CL, which is written, it is lead-free BNKT single crystals. This is amine doped BNKT crystals, and left one is a flux grown ITC superconducting bismuth 2212 crystals, which size is nearly 3 to 4 millimeter. Now, one slide is for the Chakrovsky grown crystal in our lab. I have given on the top of most of the slides some references. These references are the publication by our lab, and because they all belong to our publication, I have not given the name of the authors. They all belong to our work. And one slide is for various nanoparticles which we have grown in different morphology. Mostly they are Giordano crystals with different dopings. In some cases, they are rod type morphology like this. In some cases, this is scissor type of morphology. This is a flower shape in which we have got sheets of, instead of rods, we get a sheet of palette type of thing. And this is again Giordano, one is pure, one is some doping perhaps. And these are two photographs where a single rod of Giordano has been taken out. This dimension is hardly 20-30 nanometers. And in some cases you can find like this, where we get very sharp, it is a EDAX in which we get very sharp reflections just to show that these materials are very good crystalline behavior. Now come to nanoparticles. Uh, nanoparticles are particles whose dimensions are normally 10 nanometer to 100 or maybe 200 nanometer size. But one dimension definitely should be around 50 nanometer. Other dimension may be slightly larger than this. And if it is not a regular rod type or sheet type, if it is circular or particle type, then we can say that the structural radius should be less than 100 nanometer, so that they can qualify as a nanoparticles. So I will just discuss few things that how the nanoparticles are different from the other form of material, and what happens at nanoscale which makes them so useful, and how they are more useful for various applications. So one line is there that when we go for very small size, the quantum effects come into play, and which change the nature of the properties of the particular material very drastically. And I will discuss this thing a little bit more. Just to give you a feeling that what does a nanoscale means. That if you take a hair, a small one, it is 100 micrometer, take 100 slides, again take 100 slides, and then you will reach 1 nanometer. Here again, earth football and a fluorescence gives you a relative size of different particles or different bodies. This is again, you must have seen these photographs whenever there is a lecture on nanoparticle. Uh, I will just show you that in
Sir, voice is not clear, sir. Sir? Sir, your voice is not audible. Sir?
This, it is, can you listen my voice now? Hello?
Yes, now voice okay, sir. Continue.
No. So, this is a different development during different times. In 1981, we get STM, then we get few landmark development, particularly atomic force microscope, etc. When the real work on nanoparticles started. And of course, when we talk about nanoparticles, this is the most important line. There is a plenty of room at the bottom, which started with a challenge that can, encyclopedia can be put on the a pin size area, and this started, and he somehow demonstrated that nano size devices can actually work. Now, why these nanoparticles are so different from bulk? Two reasons normally comes into discussion. One is that nanoparticles have a very large surface to volume ratio as compared to the same mass of material in a bulk form. I will just show one slide, next one. And then that quantum effect starts to work at this small size. I will just discuss one or two slides to explain and try to make you understand. This is one slide where you can find that if I have a bulk material, start cutting it 1, 2, then 8, and then so many. So this surface area of this bulk material, you see the material remains the same. It is only divided in the smaller part, and the surface area is increasing in a big way. If a small calculation is there, that if I have a cube of 1 meter size, of course, this total effective surface area is 6 meters square. But when it is divided in such a 1 nanometer size small particle from the same volume, this surface area from 6 meters square to 6,000 kilometers square. So what happens this? That because the increase in surface area means that the atoms or molecules which are lying on the surface now can react with the outer world. So this extra reactivity makes a big change in the properties of nanoparticles. Second is the quantum confinement. That what happens that when it is size decreases, the de Broglie wavelength, then one wavelength which is coming from this Einstein formula, these wavelengths are now close to the dimensions of your particle itself, and the particle starts behaving that we have studied in quantum mechanics, that particle in a quantum box. So when your dimensions of your particle reduces, this all quantum effects start playing a very dominant role. For example, if I take different types of nanoparticles from 0 dimension that are called quantum dots to 1 dimension, where electron can move only in one direction. In 2 dimensional, that is thin films or sheets, the electron movements are confined in a plane, that is 2 dimensions. While in the case of bulk, it is in all the three dimensions. So now you see that even the density of states from a continuous in the bulk material is gradually changing. And in the case of nanoparticles, they become discrete. So there are few things which are actually taking important role to decide the properties which are changing in a material when its size is reduced to a nanoparticle size. So in the case of nanoparticles, we know that there are many changes which can take place. Color is changing, can change. Many crystal chemical properties like reactivity, melting point, then mechanical properties and optical properties particularly is changing at a uh, when the size is reduced to nano level. Of course, magnetic properties are also changing. So now what we have done till now is I have just given some ideas of single crystals, then nanoparticles. Now I will discuss a few things related to the how we grow the crystals and how we make the nanoparticles, and then I will come to the application of these things. So the energy harvesting, what does it mean? That you see that there are many form of energy which is lying unused. Particularly say I am walking on a road, so my pressure on the road is a mechanical force which is exerted on the surface. We are breathing, if wind are moving. So all these things, which is a natural one, uh, can be converted into electrical energy using some properties, particularly a piezoelectric property of a material. And then we say that this is the energy harvesting. So energy harvesting means that we are extracting energy without spending uh, anything from our side. So if we can convert a very small amount of energy which is available in our surrounding, uh, we can generate energies to work on many platforms. Many devices like mobile watch, etc., can be energized, and so on. Uh, so it is important to utilize this energy which is available in environment, because the conventional energy sources are limited, and they are depleting time with time. So we must find out something in which we can get energy without spending or without giving burden to other type of energy sources. Uh, Now, one is method is piezoelectric nano generator, in which we use the piezoelectric effect to get energy from application of a mechanical force, and we can convert this energy, mechanical energy, to electrical energy, to glow bulbs, to make so many other applications out of this energy. And now I will just define what is piezoelectricity. Piezoelectricity is the effect when we apply a force on this material, piezoelectric material, we get electricity out of it. And conversely, if I give some small energy, electrical energy, maybe AC electrical energy, we get a mechanical vibration. You can find these application in daily life. For example, in case of quartz watches, we use a small battery to get some vibration on a quartz crystal, which is converted into time because it is vibrating with a particular frequency. A gas lighter, if I apply a force, can actually give a spark and give you electricity. So when we think of piezoelectricity, uh, we define two particular property. One is piezoelectric charge coefficient. This piezoelectric charge coefficient is the gives the amount of energy when we apply a unit mechanical force, and normally it is expressed as picocoulomb per Newton. And then electromechanical coupling factor, that is how much electrical energy which is generated can be actually utilized for real applications. Higher the value of piezoelectric charge coefficient, we get uh, uh, higher electric output. These are some examples. I have already mentioned that it is a simple lighter. When we press it, we get a spark here. It is because of a piezoelectric material. This is quartz watches. This is the tip of AFM, that when we move the cantilever of atomic force microscope with this up and down, the roughness of the surface is actually sensed by this cantilever, which is based on a piezoelectric material. So the up and down, that is the force which is exerted on the tip, gives you electrical signal, and which is related to its property. Now, this is one slide which shows that which type of material we are using. Many people know the word quartz, which is a piezoelectric material. But in this case, the D33 value is very small, 1 to 2. Then Jadano is one material many people know about it. So Jadano is, when it is in a pure form, it is again very small piezoelectric coefficient. It is hardly 1 to 10. PZT is another one which is 400 picocoulomb per Newton. So all these material we have grown in our lab. And another class of material, that is PZ and PT or PM and PT, they are perovskite material, lead based and lead free materials. They are altogether almost 1,000 times better or higher piezoelectric charge coefficient. When they are crystals, we have grown all these crystals. So what does it mean? That if we have high D33 value, our devices will be much better as far as sensitivity and range are concerned. Uh, in short, I will try to explain that how piezoelectricity is generated in a particular nanocrystals or normal material. Uh, what happens that when you go to the atomic level, this is the unit cell. So the center of positive charges and the center of negative charges, if they coincide, then it is centrosymmetric material. But in many cases, they do not coincide with each other. So what does it mean? That there is a gap between positive and negative charge centers. So there is a dipole, electrical dipole moment. And this separation of positive charge and negative charge can be increased or decreased by external forces. For example, here in this case, you can find that a piezoelectric, a polarization vector is existing. So if I somehow change this, increase this gap between positive and negative charges by external forces, then you get a changed value of polarization, and this gives to electric charge developed at the surface of the material. Here is another one, which is a perovskite material, PM and PT or PZT, etc. Then you can find that here a positive and negative charge centers are different. So we have a voltage developed in one direction. If we can revert this thing, then you can find that this voltage developed is changed. Now come to one slide just to show that how the piezoelectric charge coefficient is so important. This is one publication, 3 years old, in which with Professor Kim, who are working on nano generators of Jadano and other materials for years. and one of my student, Dr. Manoj Kumar Gupta, worked there, and this is the results of their work with other materials. And we sent one of our material, that is BNKT. So you can find that because of the high value of piezoelectric charge coefficient, the output voltage from 4 to 5, etc., changed to almost 10 times higher value. Just to show you that all the other conditions, the working people are same, but the material of higher piezoelectric coefficient can lead to a much better. Uh, Now, this is one slide just to show that PM and PT or this class of material are actually extremely high. Extremely high means almost 1,000 times much more piezoelectric charge coefficient as compared to Jadano or lithium niobate and some other materials. I'm just skipping it. Now come to the mechanism of a uh, nano generator, which is based on uh, flexible uh, organic binders. So we have one material, NKLN, and PDMS is another material, organic binder. And with it, if I make a device, I will come to this again. But if I make a pressure out on it, so we get a signal of electric signal in one direction. And if I release this pressure, we get again a signal in opposite direction. So this is made up of nanoparticles of piezoelectric material. So in our cases, we have used various type of piezoelectric material with PDMS, and these devices are there. One slide is just to show that not only it is pressure. If I bend the material, bend the nanorods, for example, in this way, so what happens that one side is compressed while the other side is extended. And because of this compression and extension of the length, a very huge amount of pressure developed inside, which is sufficient enough to give a large value of potential drop. This is how the nanoparticles can be used in different way, even a pressure, a twisting, or if the nanoparticles assembly is rough, then movement of a particular tip of say FM can give you high electric voltage. This is how piezoelectronic FET can be generated. Now come to the synthesis of nanoparticles in which we are working. Of course, there are two different approaches. One is top down. Top down means you make a crystal or make a bulk material and then grind it with ball milling or some other techniques to get very small size particles, nanoparticles. Another one that you start synthesizing a material and take out the material when it is still in the nanometer size. Some details that how we make the Jadano nanoparticles. It is Jadan. We have Jadan Cl2 NaOH reaction, and then with this reaction we get either rods or seeds of this kind. This is the one photograph. I have already shown one photograph of different type of nanoparticles which we have grown. This is again Jadano with different dopings. So different dopings resulted in different type of morphology, and different morphology of this particular material actually is responsible for very big enhancement in piezoelectric charge coefficient. I will show some values. Before that, this is the chem analysis of different Jadano crystals with different dopings. This size, average size is 60 to 120, 30 nanometer size. and the right side to show that these are, even if they are in jumbled form, they show very good crystalline behavior. Now, this is the one which shows D3 value. These curves are called butterfly loops, which is a reverse piezoelectric effect, that we apply a electric field, a voltage, and we get a variation in the dimension, the change in the dimensions. And this is plotted, and from this we can find out D33 value, that is piezoelectric charge coefficient. And in one particular case, wide doped nanoseeds, they are seeds, not rods. Uh, we get a very high value of piezoelectric charge coefficient, up to even more than 400 picometer per voltage. Now, this is the one way of growing nanoparticles. Another way is to grow. I have already shown you that we have grown many crystals of different materials or ceramics. So these single crystals and ceramic can be ball milled, that is crushed, to get nanometer size particles. So these crystals of different materials, this is PMNPT single crystals, one is BNKT. These are the ceramics which are further used to reduce the size and get the nanoparticles. So these crystals were used to grind them and then get nanoparticles. So now, once we get a nanoparticles, how to make a nano devices? So this is the nanoparticles, maybe ZNO, maybe PMNPT, maybe some other material, but it is a nanoparticles of piezoelectric material, and we just mix it with PDMS. After proper mixing, we get a spin coater, and we get a thick sheet of these materials. And then there are more details, that how we use ITO substrate and then put our tape and then put another electrode from the top. And we get finally a piezoelectric nano generators like this. One thing is interesting, that we are giving the name nano generator, but the size of particles which are actually responsible for the output is of nano size, but the whole device is of few centimeter size. For example, if I take a tape like this, we have fabricated, and this is just showing the distribution of piezoelectric nanoparticles, which is almost uniform distribution. And there is a ITO substrate, and then your material, it is the boundary. So the upper one is much more width. So now applications of this piezoelectric materials. One thing is very clear, that if I have a material with piezoelectric charge coefficient, say 10 picocoulomb per Newton, and another one is 1000 picocoulomb per Newton, then with the same force, we can get much better output voltage and output energy. So the aim is to make devices of a material which is very high piezoelectric charge coefficient. For example, this is the demonstration of very simple demonstration of piezoelectric charge energy. Below my finger, here is a piezoelectric material sheets. It is a pallet made of piezoelectric material. If I just press it here by our thumb, you can see that it is 68 millivolts are developed. These are the electronic circuit just to make this electric output used for glowing the bulb, and other circuits are there so that this glow can stay for some longer time. Now, on the left hand side, I have written that how many other applications are possible. The piezoelectric material may be a good ferroelectric material also, a dielectric material also. So these applications are always there. I'm not discussing the applications of ferroelectricity and dielectric, high dielectric constant material. But of course, the same material can be used for other applications. This is again a similar thing. I'm just skipping it. Now, these are the some results. Now I start showing you. Time now. If this is a device, I make a press by finger, release it, we get a voltages out of it. And this is the output of a PM and PT ceramic. You can find out that in the case of ceramic, the output voltage was nearly 14 volts. But when we put the crystal as a whole without grinding it, we have achieved up to 50 volts on pressing. This is the output of uh, voltages, which is because of the pressing of your material. This is the instrument which we use. The earlier one, we have shown that we started with finger tapping. Finger tapping is equivalent to very small force like this. But for further studies, we have a force simulator. That is, we can put our devices here, a device in between these slides, and these rods from the top, it is just pressing it with his force which we apply. And we can change the tapping frequency as well. We can change the tapping force, and we can, this is showing the tapping force variation. And in the CRO, we are getting the output voltage. So we can, if we increase the, this is one in which if you increase the force applied on this from 0.4 kg to 2 kg, you can find this output voltage is changing from 3.6 volt to up to 60 volts with and these gaps are 1 second gaps. So the frequency in this case probably is 1 second. Then there are other studies that if we change the material, piezoelectric material with the ratio of different ratio of PDMS. So even this is changing the output of the device because the different concentration of piezoelectric nanoparticles in PDMS gives different output voltages. The right hand side below photograph is very interesting, that this question is always there, that if you are applying a force, how many times you can apply a force, how many times your device can sustain the application of such a large force. So this is the answer. Actually, we have done it for a large number of times, maybe a few thousand, 4,000, 5,000 times. But our screen in CRO can capture up to 700 times only. So in one screenshot, this shows that this output voltage, which is 11.7 or 8 here, is almost constant throughout the application of oscillatory force. This is the enlarged file. You can find that this top value is equidistant and almost constant output. So what does it mean? That we can change the output voltage by application of force. Even by releasing, we get force output voltage in another direction. We can get a output voltage just by, on the left hand side, you can see that if I twist the tape, we do not apply any force. We just take in our finger and bend it like this. Then even this bending can give you certain output voltage. Now we are coming to the end of this talk. In this another doping material. This is a Giordano material. Uh, uh, we apply a force like this, we get output voltage. In this particular case, we have changed again the ratio of PM and material versus the binders, and we get different voltage. This is now very recent publication. Uh, now I would like to thank you. So in summary, we have just shown that many nanoparticles of different materials has been prepared, and they are used for pressure sensor and energy harvesting. Finally, I'd like to thank my all PhD students who have worked for this nanoparticles and growing single crystals and making devices. I had a few DST, DRDO, and UGC projects for nanoparticles also and for single crystals. Finally, I welcome all of you. If you are interested to do some work in our crystal lab, you are most welcome to use our facilities. Uh, Thank you. Thank you very much.
Sir, thank you. Rice presentation regarding nanomaterials. Sir, now question session, sir. If you audience participant, you want any question, ask the sir. Sir.
Yes. Hello.
Sir. Sir, now question session, sir. Please, participants, any question?
Yes, you can ask questions.
Yes, sir. Yes, sir. Please, audience, ask questions.
I'm not listening any question.
Sir, 1 minute. Please, audience, participants, any question? Sir, in the chat box, sir?
Yeah.
The chat box or question given. What are the characteristics techniques available in our research lab? Someone asking question, sir.
Yeah, in our lab, we have electrical characterizations like piezoelectric, ferroelectric, pyroelectric. This is one. We have a dielectric constant measurement. We have a hardness measurement. We have a Hall coefficient, that is electrical characterization, IV curve and Hall coefficient measurement. Then we have micro hardness studies, and many more things are there. For growth of crystals and nanoparticles, we have both techniques. One is for chemical synthesis, all. Then for ball milling is there for making nanoparticles. And because we have a crystal lab, so we have almost many techniques, Czochralski method, Brigman method, zone defining technique, flux method, of course, solution method is there. We have a modified Czochralski method in which we are growing organic crystals of low melting point, and so on. Next question.
Sir, in the chat box, sir, using the ZNO nano rod as a conductor, what will be the range of pressure that can be used to produce piezoelectricity to generate and operate some electronics devices, and what will be the output voltage range? Will it be depend on temperatures?
I have listened. Your first few words was missing. Can you repeat initial word?
Is it
If I
used?
understand, he is asking that how much force is required to get a
Okay.
reasonable output voltage. This is the question.
Yes, sir. Yes, sir.
Yeah. So you see that in our case, we started with finger tapping, and we know that how much force we can apply through a finger. This is one. Then with the devices we have few kg forces to perhaps 5 to 10 kg forces. Uh, the target and the research is uh, for getting higher output with smaller forces. Even the works are going on that if my heartbeat is there, and if this variation in pressure in our blood pressure can generate electrical energy or not. So the purpose of all this research is to reduce the forces required to get higher output, or at least the output which can be studied and which can be used. So for this, the most important thing is to make a material which is of very high D33 value, so that a smaller force can give you higher uh, piezoelectric charge coefficient. And there is no limit that how much lesser force we can use to get a reasonable output voltage. Fine. Next question.
Yes, sir. Please, participant, any questions? Sir, one more question, sir, in the chat box.
Hello.
Sir, one more question.
Just tell me.
Can these piezoelectric materials used to synthesize thin films that can be used in the solar panels?
Can you again repeat because there was some. Are you asking that this material can be used for solar panel?
Yeah, sir. Can these piezoelectric materials used to synthesize thin films that can be used in solar panels?
Yeah, very different question. That all these materials, which is piezoelectric, are used to make thin films. But for solar panel, solar panel means that you are using the solar energy into electricity. Fine. So no piezoelectric material is necessary for this. But there are works, even we have published one paper in which a piezoelectric material has been used uh, to give you piezoelectric energy output as well as solar energy conversion. So this is a very good work to make a panel, solar panel, in which a piezoelectric material is there, so that the same panel can be used both as a source of electricity from utilizing a light energy from sun, as well as or along with a piezoelectric effect also. So this dual application is possible, and many people have published paper and worked on this. Next question.
Yes, sir. Thank you, sir. One more question. How to identify the system of the crystal? For example, whether the crystal is orthorhombic, tetragonal.
Oh, good one. Yeah, this is the XRD. If you take powder XRD, you 2D sine theta is equal to n lambda is there. So this is the very basic BSc level practical work that using a powder method, you can find out the cell dimensions, that is the ABC values. You can find out the symmetry, that is, for example, P1, 2 is there, or 4 is there, this type of space groups. You can find out the crystal class as well. This is very simple mathematics. Um, I can advise you to just go through any graduation level book on XRD or crystallography, and you will find that these things can be find out very easily, huh? Just by putting 3 or 4 peaks, the position value, that is theta value, and the corresponding d value. D is the interplanar spacing values. And then you can find out some formula. That one formula is for cubic crystal, one formula for orthorhombic. So in different
Sir, sir.
are you able to listen me?
Yes, sir. Sir, one more. Sir, one more question.
Yes, you can ask.
Sir, 1 minute. What is scope is natural plant and animal product formulation in environmental science?
Many people have unmuted them, and all the sounds are mixing.
Sir, 1 minute, 1 minute. Okay. Sir?
Tell me. You have to use a different microphone, perhaps. Your voice is with so many background sound.
Sir?
Yes, tell me.
Okay, sir, no more question. It is a really very nice presentation regarding today's topic.
Yeah, thank you very much. And I'm very happy that I have a good interaction with you all. And a large number of participants are there.
Yes, sir.
I again say that anyone who is willing to work in our lab can come to us, and there is administrative formalities. You can work and use our facilities. I welcome you all to work if you are interested. Thank you. Thank you very much.
Sir, really thank you. Thank you. Very nice present. Thank you, sir. Thank you so much, sir.
Okay, so should I leave now?
Yes, sir. Thank you. Thank you. Okay, leave, sir.
Thank you.
Please participate next session. Sir Magesh sir. Magesh sir. Sir Magesh sir. Sir, shall I start, sir? Sir. Okay, sir. 1 minute. 1 minute. Magesh. Magesh resource person connect பண்ணு. Magesh சொல்லா. Sir, now okay. Sir, okay, sir. Sir, connect ஆயிட்டீங்களா? மகேஷ் சார் கனெக்ட் ஆயிட்டீங்களா? இல்ல நீங்க கனெக்ட் ஆயிட்டீங்களா சார் உள்ள? ஓகே சார், ஓகே ஓகே. மீட்டிங் தெரியல அடுத்த ப்ரோக்ராம் ஆரம்பிச்சு அடுத்து வாங்கலாம் வீடியோ ஸ்கிரீன் வாடா ராஜேஷ். என்னாச்சு? மகேஷ் சார். சார்
ஹலோ சார்.
மகேஷ் சார், குட் ஈவினிங் சார்.
ஹலோ சார்.
சார் வெரி குட் ஈவினிங் சார். Sir, Magesh sir. Magesh sir, sir. Sir, Magesh sir. Sir, very good evening. Magesh sir. ஒண்ணுமே தெரியல வயசு அவர் பேச முடியல. மகேஷ் சார் ஆடியோ எனேபிள் பண்ணுங்க. சார் 1 minute. நான் ஓகே. ஓகே சார். கேக்குது. அவர் எனேபிள் பண்ணுங்க மகேஷ் சார். 1 minute சார் 1 minute. அவர் சவுண்ட் எனேபிள் பண்றாரு. இருக்கீங்களா? சார் நான் ஓகே சார். மகேஷ் சார் நான் ஓகே.
Are you hear me?
Yes sir, voice continue.
Screens are also enabled, sir. என்ன பண்றாங்க? அஞ்சு விவரமா இருக்கான். ஒரு கிஸ்ல எடுக்கிறது கூட சங்கர் சார் சொல்லுன்னா என்னால முடியல. ஒரு கேரக்டரிஸ்டிக் நடக்குது.
மகேஷ் சார்.
Are you hear me, sir?
சரி சார் கண்டினியூ சார்.
சார் என்னுடைய ஸ்கிரீனை எனேபிள் பண்ணுங்க. My screen is not enabled still now.
our power point. Our PPT is the
in my name you have to enable my screen, sir.
Magesh sir, share பண்ணுங்க sir.
Sir, still it's not enabled, sir.
Not enabled on the. இல்ல கொடுக்கலங்கறப்ப. என்னதான நடக்குது? சரி, நான் okay.
I think now okay. Now okay.
Okay sir, continue.
Sir, there is a screen. Could you see my screen, sir?
Yes sir, yes sir. Yes, sir.
Shall I continue?
Sir, continue.
Okay.
Continue. Sir, very good evening, sir.
Shall I continue, sir? Or you want to talk something? Okay. Good afternoon, everyone. I am Dr. Magesh. Currently, I am working as a postdoc fellow in National Taiwan University. This is an immense pleasure for me to giving this international webinar. Binay Kumar sir is, I know him when I started my PhD. I worked with him more than 1 month in Delhi University. He is an extraordinary person and one of the pioneer researcher in India. And he has given a very nice talk on how to grow crystals and what is the difference between nanomaterial and crystal growth. And he mainly focus on the piezoelectric because he is an expert in that. So now I'm going to talk about the synthesis and crystal growth of quantum material for advanced applications. I'm mainly going to concentrate on how one can grow a crystal from different methods. So as you know, the screen is not moving, sir.
Yes sir, sir, now okay, now okay. Continue.
Okay. So as professor told and explained very nicely what is a crystal. Everybody knows crystal is a periodic arrangement of atoms in a three-dimensional. And why the people are more interested in crystal, particularly in single crystals, because single crystal have a good symmetry and it behave as a different property in different directions. So that means the anisotropy is more interesting to study the physical phenomena of the every compound. So that is why the people still, even people are talking about the nanomaterial, thin film, even quantum dots, and still crystal growth is emerging field worldwide. As we all know that we in India, we are growing a single crystal and studying some basic properties. But if I I have visited many laboratories around the world, and where the people are mostly concentrated in magnetic materials with crystals. They are finding different crystals with the different phenomena like ferromagnetic, antiferromagnetics, quantum entanglement, quantum coherence, and topological insulator. So that is why the single crystal is the most prominent and still emerging field in the current scenario, and which is going to bring the another new technology like just quantum spinning to make other advanced technology in the next future.
Sir, Magesh sir, 1 minute sir. Please participants mute on your audio. Please, some noise is coming. Please.
Shall I continue, sir? Hello? Sir, shall I continue?
Sir, continue.
Okay, sir. So what are the quantum materials? We know materials. What is the quantum materials? Even people are nowadays talking about the quantum dots and the quantum confinement. So quantum material it's not a big thing. It's already we know, and we are not aware of much in particularly in India. So here you can see the quantum material which gives the exotic property and gives a lot of activity in the charge itself, so that those who are studying the quantum material about the spin and charge and orbital of this charge. So these materials are called as a quantum materials. Particularly people are studying quantum fluctuation and quantum entanglement and quantum coherence. And these days people even more interested in topological behavior of quantum materials. And also people already studied, already aware of many magnetic based devices and MRI scan and superconductor and hard disk. These are working based on the principle of magnetoresistance and other magnetic properties. So these materials called quantum materials, you can say even broadly superconductor and Dirac materials, particularly in graphene, strongly correlated materials. The compound which have a F electron bonding, and they are called as a heavy fermion materials and topological insulator. And topological insulator people again classified as a Dirac material and Whaley semi-metals and nodal lines material. These materials people call it as a quantum materials. So quantum material, which you can see from one atom to four atoms, from hydrogen to niobium, gallium arsenide, uranium alloys, and cuprate perovskites, and recently transition metal dichalcogenides. These materials giving exotic properties and giving a order property from unordered to order properties. So these materials called quantum materials. So, so, so quantum material you can find in a different dimension, like bulk materials, 2D crystals itself, and thin film materials. So we all know that bulk materials, its crystal will grow three-dimensionally, and this material gives a strong correlation properties, and heavy fermions also best examples, and frustrated lattice, and other exotic superconductor and topological superconductors. Other 2D crystals, like these recently people are working on layer materials like transition metal the dichalcogenides, and even nowadays people are working in nickel phosphorus selenide materials. These materials are behaving as 2D materials. You can easily exfoliate in the one layer, two layer order. These materials called 2D crystal materials. I am also working in the 2D crystals, and other people working on thin films. Thin films, heterostructure, you have a different layers which behave in a different manner based on the interface between the two layers. So this is the thin film quantum materials. So how to prepare quantum materials? There are many techniques available based on the materials. Like if you have a chalcogenide, you have to choose a different material. If you have a halides material, you have to choose a different technique. If it is a oxides material, you have to choose a different technique. If you take if you look at here, the solution growth, if you take solution growth, you have a different techniques like a organic solution growth material techniques, flux growth techniques, and low temperature solution growth, and hydrothermal solution growth. These are the solution techniques. If you go to vapor phase growth, people mainly concentrated on chemical vapor transport to grow quantum materials. Other side, you can go solid state reaction, you can make powder, and you can find the very small fine nanocrystals, that is called solid state growth methods. And finally you have a melt method. Most of the people working in melt method like Sokolsky, Bridgman, float zone techniques, Bernoulli, and Chiropoulos. There are a lot of crystal growth technique to grow crystals. So these are the broad techniques you can have to whichever suitable for your material. Particularly in solution growth, most of the people working in high temperature solution growth like flux and seeds, top seeded solution growth people, and low temperature, many of the people working slow cooling method, slow evaporation method, and temperature gradient method, and salt gel method also. So melt, if you take material melt growth, you have as I told earlier, Bridgman, so Sokolsky, flux method. So these are the methods. Vapor growth, you have a chemical vapor transport method. So I'm going to talk about all these technique, how to one can grow a single crystals. So before going to start your crystal growth process, first we must know the material, whether the material which having any hazardness or any, it will affect our health. We should aware of these. So for that, first you have to check the MSDS or other. You can also check in the bottle what are the dangerous they written in this bottle. So you can see here. And other thing is you have to look at the material whether react with normal atmosphere like ambient condition. Lithium is easily react with oxygen and it will form a lithium oxides. So like rare earth materials and alkaline materials is easily react with normal conditions. So you cannot load the material into any crucible. So better you have to choose any like a glow box setup. Glow box also you have two different types like argon glow box and nitrogen glow box. So mostly argon glow box people used to keep alkaline earth metals. So these are the important things you have to consider before starting the crystal growth process. And other important thing is you have to select the container, which container is suitable for crystal growth. So because the crucible will affect your nucleation, crystal growth morphology, and crystal quality. So we have to aware of this crystal growth container, which container is suitable for our growth purpose. So we can see the lot of crucibles from starting graphite crucibles and ceramic crucibles, tantalum crucibles and zirconium oxide crucibles, platinum crucibles. So these are the crucible used for crystal growth process. And also this is the table which gives you which material can take which crucible and which environment we can choose for our crystal growth process. So if you take lithium, you have to take crucible, graphite crucible or silica crucible, and you have to use argon atmosphere environment. So like that, the different element should know you should take a different variety of crucibles. So these are the table which gives you exact idea of how to take the crucibles. So this is the crucible, the quartz crucible one can use for normal chalcogenate materials. Sometimes if you use metals, metal can react with quartz, and it will loosening the hardness of the quartz. So people use pyroelectric coating on the quartz tube, and it will protect the quartz tubes. So these are the different designed for different crystal growth purpose. It's particularly Bridgman growth. And when once you start the crystal growth process, you must write each and everything, like what is a phase diagram, what is a melting point, and what temperature you kept for the crystal growth process, and how many days you have to keep. Like that, you have to note down in a proper manner. Otherwise, if you work in a different new materials, end of the day maybe you would have forgot. So better you have to note down each and everything. So now I'm going to talk about solution growth techniques, how one can grow uh, solution growth crystals, solution based crystals. For solution growth technique, you need some material. Let's say you need precursor material. And if you have a precursor material, you should choose appropriate solvent. And once you dissolve the material in the appropriate solvent, you have to make saturated. After the saturation, you have to allow for slow evaporation process. Maybe particularly room temperature, some people used to keep 50 degrees, 60 degrees. So once you fix the temperature, based on the slow evaporation, the solution gets super saturated. If you got super saturated, you will get a small nuclei in the solution. Once it's achieved in proper size, it will grow a big size crystals. So this solution growth method is a easy process, and it's not a very costly method. And also we can grow congruent and incongruent materials. This nothing will affect the crystal growth process. The disadvantage of this method is the stability. If you take out the material, you cannot keep a very long time, because it will easily absorb some water molecule and moisture, oxygen, and start to react. But even though some materials behave like that, if KDP is a good stability materials, even if you grow by solution, you can keep a very long time, and you can use for lesser applications. So this is the this is the crystal grown by Senthil Pandian sir, and other one crystal is grown by Rajesh sir. This crystal is grown in our laboratory by solution method. You can see here, this is the conventional grown crystals. Conventional grown crystal have some impurities, and also it will grow all the direction. So if you want to grow a single direction, so you can select this conventional grown crystal as a seed crystal. Then using this seed crystal, you can make very bulk crystals. So using the rotational seed rotation method, we have grown these big size crystals. This is KDP crystals, so you can use for this laser application. And also this is a HR method growth method crystals. This is a triglycerin sulfate doped with LLN material, which is grown by Dr. Senthil Pandian. And they maintained here different zone temperature. Here is a lower temperature, here is a higher temperature. Due to this higher temperature, solution got evaporated, and then solid start to grow at the bottom where you have a seed. So finally they will grow day by day. After the 30 days, they could have grown they have grown 1.3 centimeter per day. They have grown these crystals. So this is the simplest technique. One can grow any crystal to big, if you want big size crystals. So this is the cut, and after taking out the ample, you can see the morphology and the direction of the crystals. So next crystal growth method, I'm going to talk about the Sokralski method, which under the the category of melt crystal growth. So most of the electronic device, silicon, germaniums are grown by Sokralski method. After growing the crystal, they cut using diamond wire and make a thin the vapor. On the vapor, they are making chips and solar cells, so many things. It's a big process. So this is industrially grown crystals, silicon and germanium. You can see here, this is the Sokralski furnace, where you can take the all ingredient material. After that, after melting the ingredient material, you can just touch your seed material on the molten solution. The molten solution, the seeds start to melt in the molten solution. Then you can start pulling the crystal. After the long time of pulling, you can grow a very big size crystals. It's a very stable and a very high quality crystals. This is the aluminum bismuth single crystal, you can see here. So this is a crystal we have. When we are in PhD, we have grown by Sokralski method. We constructed our own Sokralski method. Me and Dr. Janelle Joseph is working in South Korea. So you can see the diameters when you from top to bottom. You can see the changing of the diameter. It's because of the rotation of the speed. If you allow the fast rotation, you will get a very less diameter crystal. If you allow slow rotation and time duration, you will get a big diameter crystals. So by Sokralski method, we have grown many crystals using the seed crystals. So this is the best way to grow scintillator crystals by Sokralski method. Next method, I'm going to talk about the Bridgman crystal growth. And Bridgman names refers the scientist who got Nobel Prize in 1946. Bridgman growth, you have a two different zone, and one is hot zone, another one is a cold zone. This is the temperature profile of the Bridgman furnace. So once you made a material, once you make a pure paste material, then you can load the material into the quartz ampule. Then seal the quartz sample, then put it in the furnace from top to bottom. If you pull down, you will get a nice crystal. I will show you that one. So for this Bridgman crystal growth, for my container is a graphite crucible. Because lithium is react with quartz tube, so I couldn't grow by quartz tube as a crucible. So I have chosen this lithium graphite as a crucible. Once load the material inside the graphite crucible, then you have to seal it. Here you can see, after putting the graphite inside the quartz tube, we did sealing here. You can also see here, after even I used graphite, you can see the lithium vapor comes out and react with the quartz tube. So that is why you have to select the proper crucibles. So this is the synthesis furnace we used to synthesize the material. Once you synthesize this material, then you have to again grind it and take a very nice conical shape quartz tube and put your material, and you can grow a crystal by Bridgman technique. So in this technique, you have a top zone. As I told earlier, you have here top zone and bottom zone. Based on the material, you can set the temperature. Let's say for my material, I set 750 per higher end, the no, zone 1 and zone 2 is a 600 degree. I said when you pulling down the material, your crucible, it start to nucleate at the bottom of the crucible, then it will grow big size crystals. So we have so many of furnaces, so that we have grown many crystal by bridgement technique. So you can see here the crystal start at the bottom of the tip, because you need a single orientation. That's why you make a very sharp crucible. So this is the material for cadmium indium selenide we have grown in my lab in India. This is some of crystal we have grown, me and Dr. Vijay Kumar, for different application, IR application materials. So this is grown by Vijay Kumar. And this work I have done in Argonne National Laboratory in US, where I have grown rubidium bismuth bromide. Basically, this material is prepared by solution growth. Once you prepare the solution material by solution method, then we dried it completely 3 days, and then we put it in a quartz crucible and filter it. Then we got some material, and that material we purify using the zone refinement method. You can see here the good quality of the material is segregated in the one end, the other impurity material segregated at the another end. So we can get the very pure material. Once you got the pure material, we can grow by bridgement method very nice crystals. This is a rubidium bismuth bromide, which is grown in US. So next technique, I'm going to talk about the float zone, optical float zone technique. This is the people called as a crucible-less technique. You can grow a crystal without crucibles. So in the optical float zone, you have a different mirror. Maybe some optical float zone you have 2 mirrors, some optical float zone technique have a 4 mirror. This all light in focus in one point where your material is pointing, and then you can start pulling down, you will get a very nice crystals. So I will tell you in detail. So you can see here in the float zone technique, is a common practice for all melt growth. You have to prepare a material by solid state reaction and make compound and conform by XRD. Once you conform the XRD, then you can make a rods, feed rod, and the people call it as feed rod and seed rod. So bottom one is mostly seed rod, top one is feed rod. Once this top end feed rod end, we have to first melt it, then slowly take the seed rod to feed rod and connect the both rods, then start pull down. You can see here this simulation diagram. This is your entire rod where you have only small zone, it's melted. Then if you pull down the material, you will get a very nice crystals. So advantage of the float zone technique is a crucible-less technique. There is no contamination of crucibles, and you can get the very high quality crystals. And also you can monitor the growth process. We can change the feed rod rotation, seed rod rotations, and also you can change the temperature. So this is the real-time approach. You can monitor each and every parameter of crystal growth. So you can grow very big crystal by using this method. And also we can grow low temperature melting material and high temperature melting materials. And some material, if it's a very high temperature like 3000 degrees Celsius, then you can use a flex. Then you can use by this technique. Some disadvantage of this material, this process is volatile material. You cannot grow like halide materials or chalcogenate materials like phosphorus, selenium, tellurium. Those material you cannot grow by this method, because once it's material it will evaporate. So this method is you cannot grow um, volatile materials. So other limitations, the reflectivity of melt. Sometimes if we have a more temperature gradient, it will reflect the materials. It's very difficult to grow the crystals. And also some constraint, you cannot maintain a very large pressure. But nowadays people start to grow a crystal high pressure floating technique also. But commonly you can maintain up to 1 atmospheric pressures. So these are the limitation of float zone techniques. So you can grow congruently melting materials, and with changing these parameters, heating powers, feed rod rate and seed rod rate, as well as translation of seed rod and feed rod. Based on this material, one can adjust and we can grow a big size crystals. So you can see when based on the rotation of feed rod and seed rod, how these melt will behave. See, you can see if you feed rod rotation is faster than the seed rod, seed rod, then you will get a conical concave structure of the melt. If you both the speed are almost same, then you will get a light concave structure. If you feed seed rod rotation is very high, then you will get a very sharp. So but this type of uh, uh, melt structure, we cannot grow very good crystals. So this is the typical picture. You can see this is at the top. You can see this is the feed rod. At the bottom is a seed rod. It will start to grow a crystals. You can see the grain boundary, everything. So to preparing the feed rod or seed rod, as I told already, we have to make pure paste. Once you make a pure paste material, then you have to make hot press or SPS, like a spark plasma sintering with surface polish. If you do this SPS, you will get a very good density of the material. Then you will get a very good quality crystals. Otherwise, when you melt the material, it will fall down very easily, because the density is very low, then easily spill out. So that is the, so you have to make very high density material feed rod. Once you make a high density feed rod, you have to sinter it around 800 degree to 900 degrees Celsius, using any furnace you can use, and sinter it, center the rod. Then you have to connect in the float zone technique. You can see here at the bottom is a seed rod, and top is a feed rod. And once they start going down, you can get a very nice crystals. So this optical float zone, people use halogen lamp sometimes, sometimes xenon lamp, which can give a temperature around 1100. Recently, people even grow crystal at 3500 degrees Celsius. Most of the crystals are oxides crystal. No, mainly people who use this technique for oxides crystals, because oxides is very refractory, so it's very hard to melt it. So that's why people using. So these are the different mirror and different companies selling the float zone, optical float zone. And this was no, they were tried in 1970s using lasers, and right now commercially people using laser based float zone techniques. So you can see here, you can tune the angle as well as the light, everything. You can change the frequency, wavelength. using this laser, we can grow a even very hard material. We can easily grow this type of crystals, but this is very dangerous. Not dangerous. You have to take more precaution, and cost of the instrument also very high. So this is some of the crystals we are growing. This type of crystal, oxide crystal, we are growing here currently, like lanthanum, strontium, magnesium oxides, lanthanum, strontium, copper oxides. We are growing here. So other technique, the fourth melt growth technique is wafer technique is a chemical vapor transport. So one of the very good technique to grow 2D materials. Most of the 2D material people are using these techniques. So here the quartz container, the crucible, we are going to maintain the two different temperature. One is hard zone, another one is cold zone. In the hard zone, we have to take our powder, the material, which already we prepared, base purity material. You can keep this end, the higher temperature end, and another end you have a cold temperature. This along with your material, you have to choose the transport agent like iodine, barium chloride. Based on your material, you have to choose the transport agent. So reactant plus your gaseous material like your transport agent, and combine together and form a gaseous state. In the cold end, you will get a very nice crystals plus gases. So when you cool down, it's all condensed. So don't worry much about this. So you can see here, and this is the like a exothermic, endothermic crystal growth process. You can commonly people use a different transport agent like iodine, bromine, chlorine. Even people use so liquid agent also, HCl and like that. So using this technique, we can grow many quantum materials. There are many problems occur while growing crystals, because if you transport rate is should not exceed the growth rate. If you happen like that, you won't get a very nice crystals. And also you have to optimize the temperature evenly all crucibles. Crystal chamber should be very large to prevent the intergrowth. In between some intermediate compound also possible. So that's why you have to maintain very large container. And these are the parameter we have to optimize during the crystal growth. So this is the crystal David Manrose we are growing now. We are here in our laboratory also. We are growing a FEP SE3 crystal and the FEP S3 crystals using by chemical vapor transport. The one disadvantage of this technique is we cannot grow a very bulk crystals. We can grow only maximum 1 centimeter crystals, I can say. So how to make these materials? The first step, you have to take your material and grind it. Let's say nickel, phosphorus, selenium I'm going to grow. So you have to take nickel and phosphorus, selenium in the glow box environment and grind it. If you have a pellet press, you can press and make a pellet, and then pellet you can take in the quartz tube, and then you have to fuse the quartz tube, like seal it, then we put it in a furnace. You have to look at the temperature also, because selenium, sulfur, phosphorus is easily create a high vapor pressure. So you have to optimize slowly. So once material is grinded material is reacted, then you have to take out and check the XRD. And once the crystal, the phase is formed, next you have to go for the vapor transportation. So the for transportation, vapor transportation, you have to take your material as well as appropriate agent, transport agent like iodine. This is the way you have to take a material, and after you take in the material, sometimes iodine easily evaporates. So some people use tissue paper and soak it in water, and while sealing they will use this one. Then that container of vapor transport crucible is mostly 30 centimeter to 35 centimeter, because you can you have to take your source material, source side, and as well as cold zone where the crystal is growing. So you need a very large space. So mostly people use 30 centimeter to 35 centimeter. So and sometimes the tube is chosen based on the temperature gradient of the furnace. So you need a 2-zone furnace. Sometimes you need a 3-zone furnace in horizontally. So this is the 2-zone furnace. So you can keep hot zone is around 800 degree and cold zone is 750. Less than that one. Maybe mostly people use 50 degree to 150 degree. They will maintain hot zone and cold zone. So you can see here how they are maintaining. You can keep your ampoule inside the furnace, and you can set the temperature, and you can, after maybe 10 days, you will get a very nice crystal. If it is not formed, we have to go another alternatives. This is a grown crystals. If won't grow, the crystal is not grow, maybe increase the transport agents or increase the temperature. Sometimes if the crystal is very small and not growing very big size, then you maybe some other phase may be formed. So in that time you can take the material and dissolve in acid and make a very pure material. Then again you put that material again in the quartz tube, uh, and keep the one side is very hot and other is cold, instead of putting a regular way. So you can make all material in one side, and you can grow it. So these are the materials which is grown in our laboratories. Other techniques, flux growth technique, it's a very easy technique, and you don't need much big instruments like a float zone. So if you have material and container and one the temperature thermal box, you can grow it these crystals. So what are the what are the things you require for flux growth method? I think professor also talked about the flux growth technique. I think you've grown many KTP crystal as well as NBBT crystals for piezoelectric application. For flux growth technique, you need a material and you need a container, and you have to seal it. Once you seal it, you have to keep in furnace, let's say 1000 degree of your material. Then keep it that material in 2 days, then slowly cool down around 600 based on your flux material. Mostly more than 200 degree, you keep them 200 degree temperature while cooling down. uh, in that temperature, what you have to do is, this is a very tricky process. When you have to take the material, that means the container, and put it in a centrifuge and rotate it very fastly. Only 1 minute. If you rotate that one, you will get crystal separate and flux separate. So that is why you can see here this ceramic crucible, 2 ceramic crucible with frit rod, cap. So it will easily, the melt will go down the other end. You will, the crystal is stuck in the frit ceramic cap. So how to do this one? So this is the quartz container. Inside you have a ceramic crucible, and you have frit ceramic, and another one more ceramic, and people put silica hole also to hold very tight. So even they will put at sometimes bottom and sometimes top. So once the material is completely melted and crystal formed while cooling down from higher temperature, lower temperature, you have to maintain mostly 200, sometimes 600. Then you take out the material and put it in a centrifuge and rotate it. You will get very nice crystals. These are the common flex people use while growing crystals. Mostly this material should have a lower melting point and it should not have a lower boiling point. So boiling point should be more than 1000 is better. Some material mostly more than 1000 is better. So most of the people use a tin as a flex. Some people use a lead. Some people use aluminum oxides as a flex. So these are the commonly used flex materials. The problem in flex growth technique, the advantage of flex growth technique is it's not inexpensive technique. It's a very easy, very less cost, and if you have a small amount of material also can grow, but you cannot grow big size crystal, of course. You need not to wait very long time. You can grow 1 or 2 days or sometimes 3 days. And also and sometimes you have some residue because of this flex deposit on your crystals. That also you can find while doing the resistive measurement, or sometimes while doing EVSM or PPMS, you will find the impurities. And these are the pros and cons, and I don't have much time I can discuss this. So there sometimes the chemical compatibility won't be good, and it will react with the container and it will spill out. So these are the problem while doing the crystal growth. One can face it. These are the reference. If you want, you can go through it and you will understand a better way of flux growth technique. So thank you for listening. I think I'll take more time. If you have any question, please ask me.
Thank you, sir. Sir, please participate any question. Sir, in the chat box, some question. Sir, what types of impurities are present in conventionally prepared single crystals? Sir, is it audible?
Yeah, it's audible, sir. In conventional, you are talking about solution growth technique, right, sir? Hello.
Yes, sir. Yes, sir.
In conventional grown crystals,
Yes, sir. Question is.
Yeah. Conventional solution growth techniques, you have many impurities, like metal particle also it will be there. It's depend on the purity of the material which you have taken. If you, let's say, if you are taking some organic material, so there could be many possible of material which can present in your crystal. And also in conventional you will have a more number of water inclusion compared to melt growth techniques. If you let's say for example, if you grow NaCl crystal by melt method, you won't get any water inclusion. If you grow by solution growth, you will get a lot of water inclusion. Then it will impact your application.
Okay, sir. Okay, sir. Please, any other participants questions? Sir, one more question in the chat box. Which best method of preparation of hybrid composites of organic biopolymers and metals, sir? Sir?
Biomolecule, I don't think so can be grown by this technique. By as per my knowledge, I can say they can grow by soil gel method. Is a good method to grow those type of biomolecules. Soil gel methods.
Okay, sir. Sir, one more question. Can we
Yes,
can
sir.
we grow diamond crystals using flux method?
Actually, for diamond crystal growth, normally you cannot grow by any ordinary method. You need a very high pressure and high temperature. So they will say that N-will diamond, there is one technique, they will use that technique only they are using to grow a diamond crystal. Any other technique we cannot grow by flux also, because you need a very, very high pressure, diamond is very hard material.
Okay, sir. Sir, another one. In which crystal growth method is best for devices using single crystals?
So you cannot say this method is best for a device. For silicon, particularly for silicon. If you take silicon, if you grow by Bridgman, you have a more number of impurity. Container impurity will be there. If you grow by Sokolsky, there won't be much impurity. So I can say Sokolsky is the best method for growing uh, silicon crystal. Of course, you can grow by optical float zone. Even it's a better technique for a device application, but that is very costly. And also, if you go for multiple, production, large production, it's very difficult to make that large scale for silicon. So I can say if you want to grow very high quality crystal, you can go optical float zone technique. It's the best for silicon crystal.
Okay, sir. Sir, another one question. How can we go for metal organic frames?
Metal organic frameworks, people are working, that's really chemistry related, but you can grow by solution method. You have to take a lot of process to make that type of material. Once you make that material, you can grow metal organic crystals. But while making metal organic framework itself, it's a very long process. They have to synthesize, they have to put column chromatography, then they have to take a number and confirm the material. Once they confirm the material which they want, then we can grow by solution method, we can grow a big size crystals.
Okay, sir. Sir, one more question. What precautions should take to prepare single crystals by the precursors sensitive to the environment?
So I told you, if you want to prepare a lithium based compound, so you have to load your lithium element into the container under the argon atmosphere. If you grow a lithium under the room atmosphere, ambient atmosphere, it's easily react with. It's based on based on the material we can choose which environment we need.
Okay, sir. Sir, one more question. Is there any green synthesis method in this field? Build?
Sir, I'm not hearing you.
Sir, is there any green synthesis method in this field?
Green synthesis means so everything we are using chemical. I can't say no, it's a green synthesis. Maybe solution. So any method, it's it's disposing the material is very difficult actually. But if I say green synthesis. Mm, Float zone technique, I could say green synthesis, because
Okay,
you are
sir.
not
Sir,
wasting any chemicals.
yes, sir. I have one more question in the chat box. Can we grow single crystals of polyaniline doped metal oxide?
Polyaniline doped metal oxides.
Yes, sir. Yes, sir. Yes, sir.
So first we have to think about metal oxides. Metal oxides, it's everybody knows zinc oxide, manganese oxides, very strong bond interaction. I don't think so. This organic material put into the inorganic environment. I don't think so. It's possible to grow that type of stuff.
Yes, sir. Sir, one more question. it is possible to grow crystals by hydrothermal method.
Which one, sir?
Hydrothermal method.
I am not talking about actually hydrothermal. Which material they want to grow?
Sir, actually this question is, sir, 1 minute. It is possible to grow crystals by hydrothermal method, sir. Hydrothermal method.
Yeah, easily can grow. I also grown many crystals by hydrothermal. The problem in hydrothermal, you can't get more than 2 millimeter size. That is the disadvantage of hydrothermal. Of course, the quartz early days in 1950s, many scientists grown quartz crystals by hydrothermal only, but that is a big container. But in our lab scale, we can grow maximum 2 mm, sometimes 3 mm crystal only we can grow by hydrothermal. We can grow also, of course. Many crystal we can grow. Oxides crystal we can grow by hydrothermal method. Some chloride based, halide based crystal we can grow by hydrothermal. Some nanoparticle also people using hydrothermal. So you can grow by hydrothermal as well.
Sir, one more question. Which method is best to prepare TiO2 titanium oxide quantum dot?
Sir, I'm not hearing your voice clearly.
Sir?
Sir, I'm not hearing your. Yeah.
Sir, which method is best to prepare? Yes, sir. Sir, which method is best to prepare titanium oxide quantum dot? TiO2.
So quantum dot is actually nano material, or you can say that's a low dimensional material. Titanium oxide you can people mostly prepared by Sol-gel method, and some people prepare by hydrothermal. I think hydrothermal Sol-gel they can prepare quantum dots, but they have to select the appropriate precursor material, and they have to maintain. Mostly people use 120 degrees centigrade, and some people use 150. So based on the temperature, it may change the particle size.
Okay.
So
okay,
I think
sir.
hydrothermal and Sol-gel method they can grow.
Yes, sir. I have one more question. The GS means Socrology is available in India.
See, that Sokolsky method is available, sir. In NPL, National Physical Laboratory, they have a Sokolsky method, and in our where I did PhD in SSN College of Engineering, Professor P. Ramasamy having a Sokolsky method, but it's not highly sophisticated. But that is our own constructed furnace. We can grow a crystal using that Sokolsky.
Sir, very nice, extraordinary presentation, sir.
Thank you, sir.
Magesh sir, really thank you very much for our excellent presentation today topic, sir.
Thank you, sir. I am also happy to deliver my talk. This is first webinar from outside the country, so it's a nice time. Thank you for.
Sir, most of the participants are mentioned the word is it is a very nice presentation, Dr. Magesh.
Okay, thank you, sir. I'll thank to all of them.
Sir, now, yes, sir. Thank you, sir. Now, session is going to vote of thanks.
Okay, sir.
Magesh sir, thank you very much, sir.
Thank you, sir.
Yes, the Honorable Chief Guest, respected principal, and all the participants, it my privilege to propose vote of thanks on this occasion. I wish to explain my gratitude to our management for giving us an opportunity to organize this event. I'm very grateful to Principal Dr. Nagarajan and Dr. Doni Melvin, Director of course, for providing encouragement and support to conduct this webinar. I would like to extend my special thanks to Professor Binay Kumar and Dr. Magesh Murugesan for wholeheartedly accepting for the speakers for today's webinar. The way they explain the topic as exemplary, once again I thank them for sharing their precious knowledge. My heartfelt thank to Dr. Narayanasamy and Dr. Subramanian and Dr. P. Selvarajan and Dr. Muthu Sandil Pandian, SSN College Research Scientist, Chennai, and another one, Dr. Ramalingam from Assistant Professor, Nanotechnology Department, Karaikudi, for their blessing and guidance. I heartily thank all the participants to their active participation in this event. Thank you one and all. Thank you all the participants.
Thank you,
Yes, sir. Sir, Magesh sir, really thank you, sir.
Thank you very much, sir.
Okay. Yes, sir. Shall I?
Okay.
Shall
I
I
am leaving.
leave the meeting? Sir? Yes, sir. Yes, sir.
Thank you.
Hello, Dr. Rajesh sir, organized very well. Thank you.
Thank you.
Thank you. அந்த இதெல்லாம் எப்போ வரும்? எது டவுன்லோட் பண்ணி இது அந்த யூடியூப் வந்து இதாகுமா, ரெக்கார்ட் ஆயிருக்குமா? ரெக்கார்ட் ஆயிடுச்சா? அது எனக்கு அனுப்பிவிடு. சிஸ்டம்